Hi, I'm Iroma Moulidou from University of Massachusetts Amherst. Today I will talk about some of our new results for the problem of Fermat's mean diversification, which was introduced last year at ICDT. This is a joint work with Ragava Danki, Andrew McGregor, and Alexandra Melu. But what is diversification? Let's see this with an example. Suppose Boston is published in a tourist map, and the goal is to inform prospective visitors about different ATM locations in Boston. So, how useful would this set of ATM locations be for a visitor? We see that locations are too close together, and probably this is not exactly what we would like to show to a visitor, right? So let's diversify the locations. Here, we now see a different sample that diversifies the locations of different ATMs. And locations now are more dispersed across space. In fact, this is the max-min diversification problem, which is well established in the literature. Max-min selects a set of points such that the minimum distance across points is maximized. And as we see here, max-min selects geographically diverse locations across space. But regardless, is diversification enough? What if I now told you that all the ATMs were of Bank of America? Well, this also does not seem right. In a tourist map, different banks should be represented in the sample. Not all of us use Bank of America, and there are other banks out there too. So perhaps a set like this on the right is more useful for more visitors. Here we have different banks, and this is where fairness comes into play. Essentially, the set on the left diversifies the locations of the ATMs, but does not fairly represent different banks, while the set on the right diversifies the locations of the ATMs and fairly represent different banks. In fact, this is the Fermat's mean diversification problem, which was introduced by our prior work. Okay, let's now abstract the problem. I want us to think of different locations as points in some metric space U. When we do not care about representing different banks in the sample, we can think that all the points are gray. So let's now add colors to the points to model different banks. So here, different colors represent different banks. And now, in the Fermat's mean diversification problem, we want to select a set S of U with, say, 8 points using 4 orange and 4 blue points, such that the minimum distance across the points is maximized. In other words, we are trying to maximize the diversity of the selected set subject to some fairness constraints. At a high level, diversity models how spread out the points are in space, while fairness aims for sufficient representation for the two colors. The best approximation result for Fermat's mean diversification, which is an NP-hard problem, is a 3m minus 1 factor, where m is the number of colors. In this work, we ask, how can we improve the approximation guarantees for this problem? And the idea is to relax the fairness constraints. So here on the left, we see the problem formulation introduced by prior work, and on the right, the problem we are studying in this work. So essentially, we allow to lose some points from each color to improve diversity. In other words, previous work satisfied fairness exactly while approximating diversity, while our work approximates both diversity and fairness. And thus, we designed bi-criteria approximation algorithms for Fermat's mean. Let me now show you a brief summary of our results. We offer the first bi-criteria approximation algorithms for Fermat's mean for general metric spaces. We then show that in Euclidean metric spaces, it is possible to strengthen the approximation guarantees, while we discuss streaming and distributed implementations of our approaches. In this talk, we will focus on two of our algorithms, both of which are randomized. We will first talk about FairLP, that offers the best approximation guarantees one can hope for diversity, but only satisfies fairness in expectation. We will then talk about Fair Euclidean, that offers an 1 plus epsilon guarantee for diversity, while throwing away at most epsilon% of points from each color. Let's now see the details for FairLP. Suppose we have a universe of elements U, as shown here, and that we want to select a set of 4 points using 2 points from the blue color and 2 points from the orange color. Also, for the sake of the example, let's assume that the optimal value for diversity opt is equal to 1. In the paper, we discuss how we can guess opt using a polynomial number of guesses. We will now see how we can formulate the data selection step as an integer linear program. At the end, we will get a set with diversity at least half, while fairness will be satisfied in expectation. As a first step, we introduce a binary variable x for every point in U. We are now ready to construct the integer linear program. Our objective is to maximize the number of selected points. And note that if for a point its x value is equal to 1, then this means that the point is being selected in the final set. We also add the following constraints. First, we want to select at least 2 points from each color to satisfy fairness. This is how the constraint looks like for the blue color. So here we sum over the variables of the blue points 1, 4, and 6, and we want the sum to be at least equal to 2. We have a similar constraint for the orange color, where we now sum over the variables of points 2, 3, and 5, and again we want the sum to be at least equal to 2. Let's now see the second constraint. We want any 2 points to be at least half apart. Since the optimum diversity is equal to 1, this requirement essentially leads to the 2 approximation guarantee of the FairLP algorithm. So let's now connect with an edge the pair of points that are less than half apart. So points 3 and 4 here in this example are connected with an edge, which means that they are less than half apart. The same goes for points 1 and 2. We can now formulate constraint 2. Note that we are allowed to pick at most one of the points 1 and 2, and this is why the sum of the corresponding variables is less or equal to 1. The same goes for points 3 and 4 here. This is how the integer linear program looks like. Let's now relax it to a linear program and use a linear solver to obtain the optimal values for the x1, x2 up to x6 variable. The next step is to use a rounding scheme to come up with an integral solution. The goal of the rounding scheme is to make sure that all the points picked, in other words, the points for which we set the x value equal to 1, will be at least half apart. As a first step, we fix a random ordering of the points that have been picked from the linear program. I'm hiding a lot of technical details, but for now I just want to highlight that the points are sampled without replacement and with probability proportional to their optimal x value obtained by the linear program. I now want us to focus on the pair of points 1 and 2 here. Since we do not want both points to be picked together, when can we pick, say, point 1? Since we process the points based on the ordering we created, point 1 can be picked at some step j if point 2 has not appeared before point 1 in the ordering. Note that if point 2 appeared first, we would have picked point 2 instead. So now, based on this condition, let's compute the probability that point 1 is selected. To do so, let me define some notation first. Let sigma 1 be the position of the ordering where point 1 appears. Now, for every position j in the ordering, define aj to be the event that point 2 does not appear in the ordering before point 1. In other words, point 1 can be picked. Now, the probability that point 1 is selected is the sum of the probabilities that point 1 appears in position j and point 2 has not appeared in the first j-1 positions. By Bayes' rule, we get the following formula, while the conditional probability here is defined as shown in the slides. Of course, I am again hiding technical details as to why we define the probability of sampling point j in point 1 in position j this way, but ultimately we want the probability of selecting a point in the final set to be at least equal to its x value obtained by the linear program. This allows us to argue that fairness constraints will be satisfied in expectation for every color. This approach leads to a two-approximation guarantee, which is the best we could achieve for fair max-min. In the paper, we show how we can modify the randomized rounding scheme to guarantee 1 minus epsilon fairness with high probability by reducing the approximation factor for diversity to 6. Please check the paper for additional details. Let's now move on to the case of Euclidean metric spaces and discuss the fair Euclidean algorithm. Specifically, we focus on spaces with dimension at least equal to 2. Because if points can be embedded on line, then we saw in the paper that fair max-min can be solved exactly using a dynamic programming approach. So let's see how fair Euclidean works using a toy example. Suppose the universe of elements U looks like this, and also, as before, suppose that we want to select a set of 4 points using 2 points per color, and that the optimum value for diversity is equal to 1. The first step is to partition the space into well-separated clusters. This step will allow us to process each cluster independently to pick the necessary number of points. Ultimately, we chunk the point selection problem into smaller subproblems that we can solve independently. So let's now construct the clusters. To do so, we pick a random point, say point 1 in this example, and we now construct a cube of length W using point 1 as a corner. W is a parameter chosen so as to be able to come up with the approximation guarantees for the fair Euclidean algorithm. We proceed with constructing more cubes as shown here, until all the points belong to some cube. Observe now that points close to the boundaries, like points 2 and 3 here, can be really close together. So what we would like to do now is to remove such bad pair of points. To do so, the idea is to throw away any point that is less than half distance from some boundary in this grid. So we create some smaller cubes as we saw here, and this is how the final partitioning looks like. We now throw away the points in the gray area. So we throw away point 1, point 2, point 3, and point 4 here, and we end up with a set of points like this. A reasonable question to ask now is, how do we make sure that we didn't throw away too many points from each color so that we are able to satisfy fairness? And in the paper, we saw that with probability at least half, the fair Euclidean algorithm succeeds in finding a solution with the required guarantees for fairness. So after throwing away these points, we have a set of clusters that are separated by distance at least 1. So now points picked in different clusters will be sufficiently far apart. And this is why we only have to worry how to select the points within each cluster. Note that points in each cluster can be arbitrarily close together. Let's now see how we can find a set of points with at least 2 times 1 minus epsilon points per color that are all 1 over 1 plus epsilon far apart. The first question is, how do we know how many points we need for each color per cluster to satisfy the fairness constraints? Well, we do not, and this is why we should enumerate all the possible scenarios. And by scenarios, I mean how do we distribute how many points we need to pick per cluster. Then we evaluate whether every scenario can be true or not. Let's fix a scenario and see how this process works. For the sake of the example, suppose we focus on the first 5 clusters. We now want to pick a set using 1 blue and 2 orange points that are all 1 over 1 plus epsilon far apart. We observe that this is possible if we can find the required number of points among the first 4 clusters. In this example, we see that this is not the case. Alternatively, we could find 1 blue point and 1 orange point sufficiently far apart among the first 4 clusters. Then we could augment this set using an orange point from the 5th cluster. We observe that among the first 4 clusters, there is 1 blue and 1 orange point, points 5 and 6 here, that are at least 1 over 1 plus epsilon far apart. Therefore, we now need 1 extra orange point from cluster 5 to satisfy the constraints. Note that point 7 is at least one distance far apart from points 5 and 6 here, and thus we can add it to the final set. In the paper, we saw how to enumerate all the possible scenarios for distributing the points across clusters using a dynamic programming approach. Fair Euclidean is an 1 plus epsilon approximation algorithm with 1 minus epsilon fairness for fair max-min diversification. To summarize, in this work, we designed bi-criteria approximation algorithms for the problem of fair max-min diversification, both in general and Euclidean metric spaces. Please refer to our paper for an in-depth review of our results. I'm happy to take any questions, and I thank you for your attention.